morning, good afternoon, maybe good evening, depending on when you're watching this. So today, in this lesson, we're looking at counting systems part 2. So, in the previous lesson we attempted to start looking at counting systems, binary, octal, decimal, and hexadecimal. We looked at the value of 2 to the power of various exponents. We did some conversion from binary into denary and denary into binary, and then we attempted to do some conversions between different counting systems. So that was quite a challenging lesson, and this is no less challenging. We're looking at signed numbers today. So in this previous lesson, they were all positive. Okay, so positive 1,000, positive 10,000, positive 213, positive 42. There was nothing negative in here. Yeah, and of course, computers need to be able to handle negative numbers. Yeah, so how do they do that? Well, let's have a look. So computers add numbers very well and very easily. But how do they do subtraction? Okay, so that's also a problem. And what about negative numbers? Yeah, so in this lesson we'll explore these two issues. So let's have a look. So we've got 7 and 4. This is a 4-bit binary number, this is a 4-bit binary number, and this is a 4-bit binary number. So 7. So 1 plus 2 plus 4. So 4, 6, 7. So this is 7. And this is 4, yeah, because this signifies 1, this signifies 2, this signifies 4, this signifies 8. So this is 4. And we add them. So 1, let me make this bigger. 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 1 is 2, which is 0 carry 1, yeah. And the answer, well, this is 1, this is 2, this would be 4, this is 8, so 8 plus 2 plus 1 is 11, 7 plus 4, 7, 8, 9, 10, 11. Yeah. Okay, success. Yeah, the system works. What about subtraction though? How on earth do we do this? So again, 7, we've got 7 and 4. So this is the same, this is the same. How on earth do we subtract this? What is 1 minus 0? Still 1. Yeah? 1 minus 0 is still 1. 1 minus 1 is 0, and 0 minus 0, what does that mean? Yeah, so subtraction is quite messy. So, there are 2 main approaches to solve this problem. There are actually more than 2, but we're going to look at the most significant 2 approaches. So the first approach is called sign and magnitude. So way back in the 1960s, 1950s maybe perhaps, yeah, engineers started to grapple with this problem. How do we account for negative numbers? How on earth do we do some simple subtraction? Yeah, and this was the first very elementary approach. What if we use the leftmost bit to signal the sign? Okay, so we use 0 for positive, we use 1 for negative. So plus 7, so anything that's positive has a 0, has a leading 0. Anything that's negative has a leading 1. Yeah? And we'll call this the most significant bit, or the MSB. And these other bits, we'll call them the magnitude bits. Yeah? All right, so fine. All right, it's not a stupid approach. Let's run with it. Let's see if it works. Yeah? So we've got some 4-bit binary numbers here. So this is all signed binary now. But this is the first problem we've got. We can see we've got 2 values for 0. Yeah? Now, if we went with this approach, this would be a huge problem for engineers, because checking for 0, you would have to do twice. You would have to check for positive 0 and check for negative 0. Engineers wouldn't like that one bit. Yeah? So that's the first problem. Let's see if there are any other problems with it. So let's try some simple addition. 2 plus 3. So this is binary 2. So this is the most significant bit. here, and these are the magnitude bits, so this is 2, and this just means positive, and 3. Okay, so this is 3, 1 and 1. So 0, 1, 1 is 3. So let's try and add these. So 0 and 1 is 1. Okay, good. 1 and 1 is 2. So that's 0 carry 1. 0 and 0 and 1 is 1. And then this is just 0. This stays as 0. Okay, and 2 plus 3. So this is 4 plus nothing plus 1. So that's 5. Okay, super. Yeah, seems to work. Well, it works so far. Now, what about this? What about 2 minus 3? So this is plus 2. Now, minus 3. Yes, we want minus 3. So we take minus 3 from here. 1, 0, 1, 1. 1, 0, 1, 1. And now we're just going to add these numbers together. Yeah? Because this is minus 3. And this is plus 2. We can just do a simple addition on these. So 0 plus 1 is 1. Okay. 1 and 1 is 2, so 0 carry 1. 0 and 0 and 1. 0 and 0 and 1 is 1. And 0 and 1 is 1. So we get this. 1, 1, 0, 1. And if we use this, 1, 1, 0, 1, we can see that the answer is actually 0 and minus 5. Well, 2 minus 3 isn't minus 5. 2 minus 3 is minus 1. Yeah? So this doesn't seem to work. Not doesn't seem to work, it doesn't work. Yeah, if we do subtraction, it doesn't work. So there's a couple of problems with this sign and magnitude approach. We've got two values for 0 and subtraction. Subtraction doesn't work. What about this approach? Approach number 2, 2's complement. So we take the negative of the binary number. So the negative of the binary number represented by switching all 1s to 0s and 0s to 1s, and then we add 1 to the result. Wow, what does that mean? So, for example, so 0, 1, 1, 1. So we switch all of the 1s to 0s and all of the 0s to 1s. So 0, 1, 1, 1 becomes 1, 0, 0, 0. Then we add 1 to the result. So instead of 1, 0, 0, 0, we add 1, so this changes to 1. And the same here. 0, 0, 0, 1 becomes 1, 1, 1, 0, but again, we add 1 to the result, so we get 1, 1, 1, 1. Yeah? And here, let's have a look at 0. So positive 0, we switch all of these to 1, so we get 1, 1, 1, 1. But then we need to add 1. So we add 1 to 0, we add 1, so this is 1, 1, 1, 1. Then we add 1. Well, 1 plus 1 is 0, okay, but then we carry 1. Yeah, because 1 plus 1 is 2. And 2 is 1 and 0. So we carry 1 here. And then 1 carry 1 is 0, carry 1. 1 and carry 1 is 0, carry 1. And 1 and carry 1 is 0, carry 1. So we carry 1 out of the 4 bits. Let me have a look. Do I have the... Let me see if I have this illustrated in the answer key. Ah, here we go. Yeah, super. So, we change all of these 0s to 1s, yeah, and then we add 1. So, we change them all to 1. Okay, so 0, 0, 0, 0 becomes 1, 1, 1, 1. So we've inverted, we've changed them. Then we need to add 1. Okay, so we need to do this maths. 1, 1, 1, 1 plus 0, 0, 0, 1. 1 and 1 is 2. So 0 carry 1. So we carry 1 here. 1 and 1 is 2. Again, 0 carry 1. 1 and 1 is 2. 0 carry 1. 1 and 1 is 2. 0 carry 1. Yeah, so we're carrying into space which isn't ours. Because this is just a 4-bit number, that's all we get. The leftmost one gets thrown away. We're overflowing into somebody else's memory space when we do that. So we can see that we've got one value for 0. Well, that's a big improvement already over sign and magnitude. But what about the maths? Does the maths work? Well, let's have a look. So here we've got 2, here we've got 3. Let's try to add them. 0 and 1 is 1. Easy. 1 and 1 is 2. And 2 in binary is 0 and 1. No? So 0 carry 1. 0 and 0 and 1 is 1. And 0 and 0 is 0. Yeah? And this is 0, 1, 0, 1, 0, 1, 0, 1. This is positive 5. Yeah. What about negatives? Yeah, let's see if this works. So that's positive 2, negative 3, 1, 1, 0, 1, 1, 1, 0, 1. Okay, so now we can just add these. 0 and 1 is 1. 1 and 0 is 1. 0 and 1 is 1. 0 and 1 is 1. 1, 1, 1, 1. Oh, what's that? 1, 1, 1, 1 is minus 1. And 2 minus 3 is minus 1. Super. Okay, seems to work. Yeah. Not seems to work, it works. Yeah. And this system of 2's complement is what we use today. This is how computers store negative numbers today. Yeah, so it was a system thought up 60 years, not 60 years ago, more than 60 years ago. Probably about 60 years ago. But every computer, every device uses 2's complement today to represent negative numbers. Yeah? So it's important that we understand it. It's important that we can use it. Now, a task for you. So for each of these two approaches, okay, so for sign and magnitude and for 2's complement, try to do this maths. Yeah? What is 3 plus 1? Using this approach and using this approach. What's 4 minus 2? Using this approach, using this approach. What's 4 minus 6? Using this approach and using this approach. And this one's tricky. What is 5 plus 5? Using this and this. Okay? So, on your notebook, on some scrap paper, pause the video. When you're ready to check the answers, we will check together. Right. Okay, so 3 plus 1. 3 plus 1. So approach 1. Yeah? So addition works. For sign and magnitude, addition works. Yeah? So this is 3, this is 1. We get the answer 4. Yeah? 1 and 1 is 2, so 0 carry 1. 1 and 1 is 2, so again 0 carry 1. 0 and 0 and 1 is 1. And 0 and 0 and 0 is 0, so the answer is 4. And the same logic here, yes, we have the same inputs here, whoops, and we get the same answer out. So approach 1 and approach 2, we get the same answer, and we get the correct answer, yeah? 4 minus 2, so this is 4, this is minus 2, so 1, 0, 1, 0, minus 2, 1, 0, 1, 0, so here, yeah? If we try to add these, 0 and 0, 0 and 0 is 0. 0 and 1 is 1. 1 and 0 is 1. 0 and 1 is 1. 1, 1, 1, 0. 1, 1. Over here. 1, 1, 1, 0 is minus 6. Well, 4 minus 2 is not minus 6. Yes, this does not work. Yeah. What about approach number 2? So, 4, so this is 4 and minus 2. 1, 1, 1, 0, minus 2. 1, 1, 1, 0. Okay. 0 and 0, or 0 plus 0 if you want, is 0. 0 and 1 is 1. 1 and 1 is 2. So that's 0 carry 1. So we're carrying 1 here. 0 and 1 is 2. So again, 0 carry 1. We're carrying into somebody else's memory space. Yeah. So this is our 4-bit answer. So this leftmost bit gets thrown away. And the answer 0, 0, 1, 0. And if we check, 0, 0, 1, 0 is plus 2. 4 minus 2 is plus 2. Okay, good, that works. 4 minus 6. Okay, so that's 4 minus 6. Minus 6, 1, 1, 1, 0. So if we add these together, 0 and 0 is 0, 0 and 1 is 1, 1 and 1 is 2, so 0 carry 1. 0 and 1 is 2, so again 0 carry 1. Yeah. This is our 4-bit answer, 0, 0, 1, 0, which we can see is plus 2. 4 minus 6 is not plus 2, no. What about approach 2? What about 2's complement? So this is 4 minus 6, 1, 0, 1, 0. Minus 6, 1, 0, 1, 0. 0 and 0 is 0. 0 and 1 is 1. 1 and 1 is 2, so 0 carry 1. 0 and 1 is 2, so 0 carry 1. We're going to throw that bit away because it's out of our memory range. So the answer is this 0, 0, 1, 0. So we can see the answer is positive. 0, 0, 1, 0. The answer is plus 2. Yeah, so 4 minus 2 is plus 2. Were we here? 4 minus 6. We've jumped about a little bit. Right, so approach 2. Right. Okay, so 4 minus 6. So 1, 0, 1, 0. 0, 1, 0. Okay, I think I got a little bit confused here with this being 2's complement. Okay. So 4 minus 6. So this is 4, 1, 0, 0, 0. And minus 6, 1, 0, 1, 0. If we add these together, 0 and 0 is 1, 0 and 0 is 0, 0 and 1 is 1, 1 and 0 is 1, 0 and 1 is 1, 1, 1, 1, 0, 1, 1, 1, 0, the answer is minus 2. Yeah, so that is correct. Now this one's tricky. 5 plus 5. So that's 5, and that's 5. 1 and 1 is 2, so 0 carry 1. 0 and 0 and 1 is 1. 1 and 1 is 0 carry 1. 0 and 0 and 1 is 1, so we get the answer 1, 0, 1, 0. 1, 0, 1, 0 is minus 2. Minus 2. 5 plus 5 is minus 2. What? Okay, well, there's a reason for that, so let's explore it. So again, we've got 5 here. Now, if 2's complement works, we would expect this to work. So let's see why it doesn't. So 5 plus 5. 1 and 1 is 2. So 0, carry 1. 0 and 0 and 1 is 1. 1 and 1 is 2. So 0, carry 1. 0 and 0 and 1 is 1. So we get this answer. 1, 0, 1, 0. 1, 0, 1, 0. So minus 6. But 5 plus 5 is not minus 6. So what's the problem here? Well, the problem is that 5 plus 5 is 10. And we can't, with just 4 bits, we can't show 10. Yeah, because we've only got 2 to the power 4, we've only got these 16 values to play with. And because they're positive and negative, yeah, if we count these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 2 to the power 4, because we've just got 4 bits, the maximum we can show is 16 values. And if we have two negative, if we have essentially 2 values of 0, okay, it's the same in binary, yeah, then we can't show plus 8, plus 9, plus 10. We can't show negative 8, negative 9, negative 10 using just 4 bits. It's not possible. We need more bits, yeah, and that's why this is incorrect, yeah. Because we need more than 4 bits to show 5 plus 5. If we think about what 10 looks like, in 2's complement, then we need more than 4 bits. And this is called an overflow, and this is an example of an integer overflow. Yes, we're trying to add 2 numbers, but the destination is not big enough to hold the result of those 2 numbers. This is called an integer overflow, and this is really quite common in computer engineering. So we saw that when we try to add 5 and 5 in just 4 bits, we get the wrong answer. This shows the importance of using a data type which is wide enough. Okay, we talk about width. This is not wide enough. We need more than 4 bits to show or to hold our answer. 4 bits is not wide enough. So let's have a look at some data types. This is a good opportunity to look at some data types. So here are some data types used in C++ and some other languages. They're similar to data types used in a lot of programming languages. What I'd like you to do is to Google this data type, find an example of it, find how wide it is in bytes. The number of bits is easy, we just multiply by 8. And what's the minimum value we can store? And what's the maximum value we can store? Okay, this is a bit tricky. There's a few answers here to help you. Yeah, this will take you some time. Use Google. An example, the number of bits. Okay, number of bits is easy because I've given you the number of bytes, so we just multiply by 8. The minimum value, the maximum value. Be careful. We've got tiny int and we've got unsigned tiny int. Okay, what's the difference? Use Google to help you with that. Okay. Right, do that please, and then come back and I will give you the answers and we'll talk about this in more detail. Right, okay, so here are the answers. So an unsigned tiny int, it's the same width as a tiny int. We have 8 bits, but it's unsigned, so we don't need to worry about negative values. So instead of negative 128 through to 0 through to plus 127, we start at 0 and we go up to 255. So still, here we have 256 unique values, and here we have 256 unique values. A short integer, 2 bytes wide, 16 bits wide. Negative 32,768 through to 0 through to positive 32,767. Unsigned short int, the same size, the same width, but our values start at 0, go up to 65,535. Yeah? And this number, 65,535, we became familiar with. In the previous lesson. 2 to the power 16, 65,536 if we don't include 0. Yeah? So if we start counting at 1, then we have 65,536 distinct values. Integer, this is the range of integers, this is the range of unsigned integers. Long, okay, so this is a 32-bit wide number. This is signed, so that's very big. -9, crikey, what is that? Quadrillion or something? Unsigned long, very, very big number. But again, okay, the same width, yeah, still 32 bits wide, but starts at 0. We have 2 date time values. One of them's 32 bits long, one of them's 64 bits long. Starts the 1st of January 1970. We will have a problem in the year 2038. Any embedded systems, any systems that are using 32 bits to encode their date time will have problems. Most systems will have moved to a 64-bit, or most systems have already moved to a 64-bit representation of date time values, which means we can store 290 million years in the past and 290 million years in the future. So using 64 bits for date time is necessary to avoid problems on January 20th. Boolean is a binary value of 0 or 1. So let's see what this means. Yeah. So if we try adding 2 big numbers and we don't allocate a big or wide enough variable for the answer, we can expect to overflow. And we saw that here with 5 plus 5. Let's have a look at another example. So we've got 127 and we've got 127. Yeah. So 1 and 1 is 2, so 0 carry 1. 1 and 1 and 1 is 3, so 1 carry 1. 0 and 0 and 1 is 1. 1 and 1 is 2, so 0 carry 1. 0 and 0 and 1 is 1. 1 and 1 is 2, so 0 carry 1. 1 and 1 and 1 is 3, so 1 carry 1. And 0 and 0 and 1 is 1. So we get this answer. If I can go to here. Oi, no internet today. No internet today. Or a problem on campus with internet. But if we find this is of course a 2's complement number, and we can see that it starts with a 1. So we can see already that it's negative. And if we work this out, this comes to negative 42. Because we need more than 1, 2, 3, 4, 5, 6, 7, 8. We need more than 8 bytes to store this answer. 107 plus 107 is 214. 214, we need more than 8 bytes. Yeah? So this is called an integer overflow. So what's the solution? Well, the solution is to make the number 16 bits wide, or 2 bytes wide. So this is byte 1, and this is byte 2. Yeah. So again, 107, 107. The answer is the same here: 110, 110, 10, 110, 10, 110. So this byte is the same, but now we've got all of these zeros here in the second byte, and this shows us that it's a positive number. Yeah. So even though these are all zeros, now we get the correct answer, yeah? Because we've used a variable which is wide enough. And this is a 2's complement number. If we put this into a 2's complement converter, we would get the answer of 214. Yeah. So having a variable which is wide enough to hold your result is very important. And here we've got an example of this. LS, let me move myself over here. Now I think we've got an example. Ah, yes, here it is. Wait. C-lang, IT. So here it is. Da, da, da. Okay, right, so where were we? Okay, so look at this simple C program. The output it generates, does the output surprise you? Okay, so this is C code that we will run in a minute. So we have an integer, x. So this is our upper boundary. 6, 4, 7. So if we look at our range, where's my answers document gone? Yep, so 4, 6, 7. So we're right on this boundary. We're right up here. Now, if we add 1 to this and we store the answer in an integer, what do we expect? Do we expect to get 8? 6, 4, 8. And let's try it again with an unsigned integer. Yeah? Again, the same number. We're going to add 1 to it. Do we expect to get the same answer? Well, let's try. Okay, so I've compiled that code, and I get some warnings. I get some warnings that it's telling me about a potential overflow, and it tells me already that I've got an overflow. So, how do I run this? Okay. So let me make this a bit bigger. So x is now negative. Yeah? So x is now negative because we're storing the result in an integer. Yeah, and an integer is not wide enough to add 1 to this. So we've overflowed, we've looped around. But if we have an unsigned integer, is my answer gone? If we have an unsigned integer, we've got plenty of spare capacity. Yeah? So when we use an unsigned integer, now I think I've actually... I think I'm actually adding 2 and not 1. Let me just check this. Where's my code? Here it is. Right, okay, yeah, so I'm actually adding 2 to the result, not 1, as it shows in our workbook. Yeah. So when we add 2 to this, should it be this? Well, it can't be, because integer is not wide enough to store the answer to this. But when we use an unsigned int, we do get the correct answer. Yeah. So we've tried to add 2 to it, we've overflowed into a negative, but here we've tried to add 2 to it, and 747 plus 2 is 49. Yeah, so that's no problem. Because an unsigned integer has a range which allows us to store that number, we're fine. If we just use a regular signed int, we can't add 2 to it or even 1 to it. We overflow and we get a big negative number. And here we can see the maths. So this is the number. We try to add 1 to it, and this is the answer we get. And this is, of course, a 2's complement number. It's quite difficult to see here. And this is an example of an integer overflow. Integer overflows are very, very common. Yeah, and a lot of professionals continue to make integer overflow mistakes. For example, here, Gangnam Style. For a brief period of time, it had negative number of views, negative 2.1 billion views. Yeah, and here's their reason. We never thought a video would be watched in numbers greater than a 32-bit integer. Yes, so 647. So they used a 32-bit integer to store the number of views for a video. We never thought a video would be watched in numbers greater than that, but that was before we met Psi. It's been viewed so many times we had to upgrade to a 64-bit integer. Yeah, so now they've changed from a 32-bit wide integer up to that's not correct, is it? That should be 64 bits. Yeah, this is 8. 8 times 8. This is 64, and this is 64. Yeah. Okay, there's 2 mistakes there. So they've upgraded to an 8-bit. To an 8-byte or a 64-bit integer, and now they can store views up to this range. Yeah. It begs the question though, why do they continue to use a signed integer? The number of views on a video is never going to be negative. So why use a signed integer? Why use a signed integer in the first place? If they had used an unsigned integer, they wouldn't have hit this value. They would have hit it when it reached 4.2 billion. Here we've got some examples of integer overflows. Gandhi, a character in Civilization, he went on the rampage. That was a result of some integer overflow. A woman thought she had won 43 million on a slot machine. That's an integer overflow. Boeing 787 Dreamliner needs to be restarted every 40 days, otherwise there's an integer overflow. The year 2038 problem with the date time, the 32-bit date time problem, that's a problem. WhatsApp introduced, increased the group size limit to 256 people. So that's as a result of hitting one of those boundaries. Yeah. So it's not clear why WhatsApp settled on such an oddly specific number. Well, it is, because 256 is a very specific number. It's an unsigned tiny int. It's the maximum numbers that you can have with an unsigned tiny int. There was an example of a space shuttle traveling at 30,000 miles an hour that decided it didn't want to go that way at 30,000 miles an hour. It wanted to go that way at 30,000 miles an hour, and broke up. It exploded. So these are very, very real examples of integer overflows that have affected real people and real software in the real world. And it's as a result of not allocating a variable that's wide enough for your result. Yeah. Okay, so that code, this code that I showed you is on Schoology. You can run it on your system. To run it on Mac, you need to use clang and then run the executable. On Windows, please use Google to figure out how to better run that. Okay, well, I hope this has been useful for you. See you in the next lesson when we will be tackling the ASCII table. Okay, bye for now.